So we have learned some data pre-processing techniques, and now we're going to apply some of them on our police shooting data. So first I called two libraries. You can just, instead of use the player, you can just call tidyverse. That covers the player, and ggplot. So again, remember that we have when we're doing our know our data exercise, we have saved the shooting data into shooting /_ original and our data. So now we can actually go back to our directory and load this file. And now we have this data set, and we can take a look to refresh our memory. Well, those warning messages is irrelevant, and we can ignore them. So run this, load the file, and now we can use the string method to get an overview of what is in shooting data. So remind us, we have body camera, yes or no, ID names, okay. And then we can still, one of the major things for every, I think for every data set, the first thing you want to do is to check missing data. And we ran this command before, and we can actually run it again. And see, we have 118 rows has some NAs in it. And now we can count how many exactly are there. 815 is quite a bit. We have a total of 4,000, around 4,500 rows. And so we want to see which columns have the most, how the missing data are distributed among columns. We ran this method before in knowing our data exercise, but applies this function to each of the columns of this data set, okay? And then we piped this to sort the counts. Okay, so we will do that, and this we can see race has the greatest number of missing values. So in the data pre-processing steps, I typically don't do any imputation task to fill the data, because especially for this class, we are going to use this example to run a whole number of algorithms, and each algorithms deal with missing data differently. So sometimes we don't need to do anything. Other times we might want to fill the data. So at this time, we know the extent of the missing data would be sufficient. And also in our examples, filling data is actually fairly challenging. So I probably would not, unless I know lots of, have a thorough understanding of the domain. And here, the numerical, we don't have lots of numerical data. If we look at our types, numerical data is the easiest to impute, to compute the mean, to fill this. But here we only have the age as the column that's numerical. I mean, yeah, the ID is really not numerical, even though it's numbers, right? We know that. Imputing age, because age, as we're going to see later, is actually quite informative in this data set. So imputing a fairly critical piece of the attributes is not a very good idea, because we run the risk of bias of our understanding. So my conclusion after the above thoughts that I present to you is to just leave out the missing data in the following analysis. If we have other ways to find those missing values, because I know this is not the only data set that's collected on police shooting. Guardians also collect a data set. We could do, if we could find the other data set, we can compare those and see if they have overlapped observations, and we can probably find age from those data set. But at this time, with this data set alone, I think it's too risky to modify the age column. And race, again, it's something that we're going to actually make lots of predictions on race. This race can be, in many cases, in our following analysis, going to be considered as a class label. And a class label, obviously, is not something that you want to impute. So now we have an understanding. We have quite a bit of missing data, but I think we're probably going to just take the rest of the observations that without missing data to do some of the computation. Besides, some algorithm can make use of those rows with incomplete data. So it will ignore the missing data, but still using what is available. So still, it's not fully lost it for any observation that contains a missing value. Okay. So when we look at this, we also see that age is a numerical value, and it has obviously we can consider this as a continuous variable. Although in this case, well, the key observation is it has many unique values. So if we do unique, our shooting data set, so we can see we have quite a number of unique values here. Therefore, this attribute have too high a cardinality for some algorithms, for example, decision tree. So I'm going to bin it. So discretize this variable. We're going to keep the original age as a continuous variable, but also we're going to use the discretized age for some exercises. Therefore, we're eventually going to have an age column and then a binned age column in our data set. So we can take a look at the distribution of the age. If we run ggplot, so we can see it's skewed, and we already know that, right? More cases happen with younger people than older people. We can do a box plot that confirms our finding that we have quite a number of outliers there, but the data is skewed towards the lower end, so it's right skewed. And we can do a summary to get the mean median, the 5-number summary that we have. And this result again confirms our initial finding that the age column is skewed. So now with this data set, how can we bin this, right? So we could use the heuristic rule. We're going to try that. So this heuristic rule that we have introduced in the class, and we're going to try that. So I use parentheses around width. So when the value is assigned to width, and but we used parentheses, then the value will be displayed right here in the output, so it's easier for us to see. If this width, using this heuristic, we got this width, and then we can find if we do an equal width bin. We can find the number of the bins that we want to create. And this n tells us to bin the data to create 38 bins. So this number tells me that this heuristic is good for histogram and data smoothing purposes. But for discretization, our goal is to reduce the cardinality of the age. Having 38 different values are still too high for some of the algorithms. For example, decision tree, it will make decision tree really, really slow. So therefore, we give up on this idea. We move on to a fixed equal width cut. So we can use 25 as an interval to cut them. So the reason that I use 25 is because according to biology, one of the theory that younger people often makes mistake that they regret is because their brains are not fully developed. And a scientist tells us that brains are not fully developed, especially the logical reasoning part, it's not fully developed before the age of 25. So I'm going to use 25 as a way to create equal width cut. So cut, it's in your R exercise. It can help us to create equal width cut. I tell it how I want to break the data every 25 years is a break. And I know the range, the range is 91, so 100 would cover that. So I tell the system how to label my new grouped age data. So I run this. You can see the data age group now have the labels that's young and old, grown and mature, right? So that's one thing we can keep. The second method we can choose is to use clustering, which is also introduced in class, and we can try that. So first of all, we need to find all the age that's not a non-value. So, and then we're going to run k-means. K-mean is one of the probably most well-known and widely used clustering algorithm. However, in this class, you're going to learn that k-means has all kinds of problems. It's most intuitive, most widely used, but it definitely has lots of problems. We're going to use k-mean as one of the simplest methods to just discretize this one-dimensional data, the age. We want to create 4 centers, and then which means we're going to create 4 clusters, and k-means going to find that the values that's closest to those 4 centers. It will iteratively to find those 4 centers that best partition the data. Okay, details, we're going to cover the detailed algorithm of k-means later in chapter 10, clustering analysis. But at this time, you can think of k-means as being cutting this line, the age range into 4 groups that each, the points within the groups are similar to each other. Points cross groups are not that similar. Okay, so we're going to run the k-mean, and we're going to use the table to calculate each of the cluster, how many values are in each cluster. As we can see, because the data was skewed, our k-mean result is different from the slightly different from the previous result. We can look at this k. So we first calculated in the 4 clusters how many observations the cluster contains, and now we can find the center of the cluster by using $sign centers. So we can see the first group have a center of 24, and the second center is 35. The third center is 63, and the fourth center is 48. So this is compared to what we have. It's close, but not exactly the same. For example, our 50 year 50 group probably is being split between 35 and 48, right? So different binning method are going to give you different result, and which one makes better sense at this time we don't know. But we can keep them and keep on thinking about them. And then we can plot this to see. So the index are the observations. So we have over 45, close to 45,000 observations. After removing the missing value, we have those age and indexes being basically this is a scatter plot to show us how different data points being grouped. So we can see that here we have anything between 0 to probably 30 in one cluster, 30 to 40, maybe 40, I don't know, 42 second cluster, 42 to 58 another cluster, and anything above is another cluster. So this is based on how the age are close to each other. So K-means is a purely distance-based algorithm. And now we can to see the exact range, we can actually do this. Oh, sorry. Here, I need to run this first. To see the exact range, we can actually do this age cluster and have the system print out the minimum and maximum range. So this is already what is shown here. We just want to clearly show you how to get the range of the clusters. So what do we do here for each of the cluster? What we did is to concatenate those and print it out. So cluster, for every cluster, we have something like that. And the starting brackets, and find the minimum for this cluster in the age cluster. And then find the maximum. And that gave us this output. It's going to be helpful for you to look what's in the age cluster. So what we can see, age cluster, what we did is we merged age and the cluster label. So every observation now has a cluster label. And now here we can find the minimum and the maximum for for the range of each of the clusters. Okay, so we did the k-means cluster, and now we can also use decision trees. Remember in the class we used the weather example to show that some attributes are more important than others. And now here we can also use the decision tree to help us bin. Again, decision tree, the detailed algorithms we're going to study in the future lectures. And here is just a quick peek and see how it can be used also for binning discretization tasks. I'm sorry. So we have we can use this is the decision tree algorithm. We use our part. So this basically says recursive partition. Okay. So we want to use age to predict race. We want to see how this race gave us information, does age give us information to predict the race of the victim. By using this, we use the class label race to try to bin age so that the correlation between age and the race label going to be more correlated. Then our data is this. We're going to use the parameters. How do we split? We're going to use information gain. We're going to talk detail about information gain and a whole set of other measures that decision tree use. This information gain is just the most typical choice. And we want the tree to have a maximum depth of 3. So this is going to generate a tree with 2 levels. And we're going to use this decision tree as a classification, not regression, because decision tree can also be used for regression analysis. So let me call this library and then build the tree. And I call another library here to actually help us to plot the tree. So this is our tree. So based on this this prediction, so how age is correlated with race. So this shows that if this is our initial data set, 100% of the data set are showing here, and those sets of series of numbers give us the distribution, the percentage of different race in the data set. And if we don't have any information, if we only have this node, then the algorithm is going to predict the victim is white, because white is here. It occupies the greatest amount of victims. Okay, then if we cut age using this 44 as the cut point, if the age is smaller than 44, then we most likely we move to the second level of the tree, and this second level, this node covers 70%, 73% of the observations. Age greater than 44 covers the rest of the 27%. And here the race distribution looks like this. We can see white people is dominant. So greater than age 44, most vast majority of the victims are white. Okay, age younger than 44 still are white. White still have the most prominent distribution. However, we can see this and this is also very prominent. So we need to actually tell us what's the so we need to actually see the to see how those map to our race. So I did a table shooting run race. So we see the first one is A, second one is B, the third one is H, third one is N, O, W. Okay, so white is still the most prominent, but also Black and Hispanic is also represent a substantial portion of observations in this node. And then decision tree further divides this based on age. And now we can see the decision tree picked 26 as the cutting point. Here we can see now Black victims is actually greater than any of the other. So here at this level, we have 22% of total observations in this node and 51% of total observations in this node. So this is still more white dominant, but here we can see that more victims. If we talk about victims younger than age 24, the majority of them were Black. Okay, so this is how we can use decision tree to find those cutting points. basically 0 to 26 and 26 to 44 and 44 and above, going to correlate with our race distribution the most. So therefore, our cut's going to be like this, okay? So again, keep this in mind, and we can move on to our next method, which is chi-merge, and we discussed in detail of chi-merge. So this also tells you that why I don't want to impute that age, because I think the age carries a main signal there, and I don't want to mess up the signal by artificially insert data into the data set. Okay, so I'm going to add this discretization library. So first of all, we cannot use anything with NA values. We have to remove those. So we created the age and race. So let's look at AR. So this is age and race. Right? We only have two columns here. We pick out this. So for every rows, it cannot have any missing values, and we pick out the column age and race from this data frame. And with AR, we can create another data frame. And I tried that. chi-merge doesn't work directly on AR, so I have to wrap them again in the data frame. So I do that. And here I can run chi-merge. I give the significance level. Remember, 0 point chi-merge does lots of chi-square tests, and it needs a significant level to decide whether the interval and the class label were correlated. One thing I also want to mention that this is also the one example that we can show that when in data mining, when we use statistical methods, for example, chi-square. Chi-square is a parametric method that assumes certain distribution, and chi-square does not work when your data cell have values less than 5. Remember from your statistics class, 80% of the at least 80% of the data cell need to have expected observation to be greater than 5. However, in data mining tasks, we don't check those assumptions. We use those statistical methods to guide the algorithm, and they often seems to be working, and so we don't actually follow the strict procedures as you do statistical analysis. First step, you check all the assumptions. And we can see in the example, especially at the very beginning, our interval and class label contingency table have plenty of ones and zeros. In that case, ideally, we want to use the Fisher's exact test. However, chi-merge use chi-square test and still achieve good results. So we're happy. That gives you a clue to understand the difference between inferences made by statistic analysis and the inferences made through machine learning methods. We have more of a practical goal of finding the patterns, even when the data may not actually conforms to all the assumptions required. Okay, that's all for that point, and now we can actually run this chi-merge. And show the cut point. So here we have the cut points produced, and we can compare this to what we had before. And here we have 26 and 44. So what we see here is chi-merge gave us a more detailed cutting. It's roughly mapped to 26 and 44, but it has additional between 44 and 47 there is another cutting point, and under 22.5 there is another cutting point. So we now start to see there is some commonality with the discretization result. So if we do that, we can see, run this, we can see how this data observations are distributed among those 5 bins. So we have 4 cutting points that creates 5 bins, right? So at this time, my decision is to probably use these finer cuts from the result of the chi-square. Chi-merge, because it we can 5 is not too big a number. For discretization, typically our result is going to be like between 5 and 9 groups. 11, 13 are probably also acceptable depending on your computational resources. But 5 is certainly a good reasonable sets of groups. 3 would be too small by my consideration, because that would lump too many data points in one group, and that obscure the potential differences. Therefore, I'm going to use this. I'm going to do the cut based on this, what we have found, the cutting points, and add that to our shooting data set. So now in addition to the age fields, I have a new age grouped field. So we can run this, and then we can take a look at shooting data, and we have the age, old, mature, young. Depending on the algorithms that we will test in the future, we might choose to use age group. We might choose to directly use age as our attributes. So now we have age group produced and stored in the data set. This video is getting long. I'm going to terminate this and start a new one.